Hello everyone, this is Professor Pawan, and in this video we are going to discuss the uh, bending equation. And the bending equation basically consists of the two parts, and the first part of that is the relationship between bending stresses and radius of curvature. We are going to derive the relationship between bending stresses and radius of curvature. And now let me explain you this diagram. This diagram is nothing but a portion of a beam with the thickness of dx, which is subjected to pure bending moment m as shown in figure. Now here this line in the middle, it represents the neutral axis, and it is called so because the neutral axis does not have any stresses on it, neither tensile or compressive. It basically is neutral, so that's why it's called as neutral axis. And AB is one of the layer which is on the neutral axis. Now consider one more layer at a distance of y from AB, that is CD. Consider one more layer which is at a distance of y from AB, which is layer CD. Now what I will do is, when I apply the bending moment like this, what happens to this straight beam? It will get bended like this, and when it gets bended like this, we can say that it forms a portion of a circle, or basically it forms an arc like this with the radius of curvature r. Okay, and let the layer lengths, which were initially AB and CD, let them be A dash, B dash and C dash, D dash. You can see that they've got bended a bit, and let theta be the angle subtended by the arc with the center. Okay. Now in this second diagram, that is after the beam has been bended, you can clearly see that the layers which are above the neutral axis are subjected to compressive stresses, that is here, and the layers which are below the neutral axis are subjected to tensile stresses, which is shown here. And exactly same is shown in this particular diagram. Here you can see the compressive stresses above neutral axis and tensile stresses below neutral axis. Now here let r be the radius of neutral axis layer A dash, B dash, this one, r let it be the radius from the center to this A dash, B dash. Then let theta be the angle subtended by the arc, and let m be the constant moment which is acting on the beam. Okay. Now for this particular problem, we can say that the strain, or we'll consider this layer CD, we'll consider this CD, layer CD, and we'll consider the strain with respect to layer CD. Now with respect to layer CD, the strain which is represented by epsilon, we can write it as change in dimension of CD by original dimension of CD. Okay. Now the change is nothing but the difference between the original and the one which is bended. Now what I can write is, I can write this as CD minus C dash D dash divided by CD. Okay. So this becomes 1 minus C dash D dash by CD. Okay. And if I want to write this in terms of the arc length formula, I can write it as 1 minus r minus y into theta divided by CD is nothing but the AB itself, which is here the similar A dash B dash, I mean this the same thing, which is r into theta, the unchanged one. Okay. Now if I simplify this, what will I get? I will get r theta minus r theta plus y theta whole divided by r theta, or simply I can write implies epsilon is equal to y by r I can write epsilon is equal to y by r and here the r which is radius is constant, and hence this epsilon is proportional to the distance from the neutral axis. That is, we can say this the strain here is directly proportional to this distance from the strain is directly proportional to this distance from the neutral axis. We can write epsilon is equal to y by r like this. Okay. Now, also let sigma be the bending stress in the layer, okay, and let E be the modulus of elasticity or Young's modulus, and hence what we can write from Hooke's law. From Hooke's law we can write from Hooke's law we can write sigma is proportional to epsilon, or sigma is equal to E into epsilon, okay, and here what will be the epsilon, we can write sigma is equal to E into epsilon, and we know the value of epsilon. Epsilon we have found out to be y by r. So, sigma I can write it as E into y by r. Okay. Hence, what I can finally derive here is, I can definitely write from this sigma by y is equal to E by r. This is the first half of the bending equation, which gives us the relationship between bending stress and radius of curvature. Which gives us the relationship between bending stress and radius curvature. Here sigma is bending stress, y is distance from the neutral axis, E is Young's modulus, and r is radius of curvature. Thank you. We will solve the next part of the derivation in next video. Thank you.